Yes, good morning, everyone. Thank you for inviting me. It's a great pleasure to be here. So let me just say, I work at the overlap of quantum theory and statistics and probability. So there is also an overlap with operator algebra and all that. So I hope you might find some interesting topics to investigate from my talk. So what I'm going to talk about is recent work with Federico Girotti, who was postdoc in Nottingham. Now he is at Politecnico Milano. And Alfred Godley, who was my PhD student, so he graduated now. And so the title is very long, but it's like a recipe for how to solve a certain problem. And the problem is to estimate parameters of quantum Markov chains optimally, so with the highest precision. And we are going to show that we can do this using something called coherent absorbers. And we sort of treat the data from the measurement data using some procedure called pattern counting. Okay, so let me start the plan. So basically, I'll tell you about estimation with IID models, so independent quantum systems prepared identically, and then I'll move to the quantum Markov setting. Okay, so what's the typical quantum statistics problem? You have a quantum system that is prepared in some state rho, and this state depends on some parameter theta that is unknown, and you want to find what is this parameter. So you can't just look at the system. You need to do a measurement to get some data. It has some probability distribution, and from this data you do something to get an estimator. Yeah? So in statistics we talk about statistical models. So the family of states, that's the statistical model, and it depends on some parameter. So in my talk, the states will always be states on B of H, but there is no problem considering more general setting of quantum models on arbitrary von Neumann algebras. But here I'll talk about states on B of H, and I represent them in terms of their density matrix. So probably a more familiar way of saying what the state is would be this, right? This functional on operators. So I'll be always talking about density matrices, and actually most of the time we'll have pure states, so one-dimensional projections. Okay, so what is quantum about this kind of problem? Well, if you fix a measurement, that means you basically fix the probability distribution of your data. So that's what statisticians do. They have some classical model, some random data with some probability distribution, and they want to estimate the parameter theta. Once you fix a measurement, it's just a classical problem. But what's interesting about quantum statistics is that you can choose how to look at the quantum system. So there are various measurements you can perform. They all give you different probability distributions of outcomes. They depend in a different way on the parameter. So there is the question, what is the optimal measurement? And for that, to find that, you need to understand the structure of this statistical model. So how is that, what's that manifold or whatever set of states is in the space of states of my system? And there is another aspect which I will not talk about, but this is very important in what is called quantum metrology. So people try to use this setting to estimate parameters with very high precision. And in that case, the question is how to encode the parameter into a quantum state such that it contains lots of information about that parameter. Okay, so now just to make more clear what I mean by measurements. So for me, measurement will be just a map from states to probability distribution on some measure space of outcomes. And this probability distribution is of the form trace of rho theta with some positive operator ME. And this M of E, this set of these positive operators, this is called a positive operator valued measure, POVM. Okay? And you can transform this into a map from T1, so you can think of it as a map from T1 trace class operators to L1 of omega sigma with some reference measure mu. So rho theta goes to p theta, which is dp theta d mu. Something like this. Yeah? So that's the kind of problem. Okay, so now if you look in the quantum metrology literature, every papers there's a huge number of papers, and all of them start with this quantum Kramer-Rao bound, because this is the most basic result, and it tells you roughly how well you can estimate a parameter. So you usually have this kind of dependence on a finite dimensional parameter, and you assume that this dependence is smooth in some way. And now you do a measurement M with some outcome X, and you are looking for unbiased estimators. So that means that the expected value of this random estimator is equal to theta. So that's an assumption, and you don't need to only use unbiased estimator, but under this assumption, the covariance matrix of this estimator, so basically this is like the mean square error of the estimator, is always larger than, and there are two inequalities. So the first one is the inverse of the classical Fisher information associated to this classical statistical model. So that's something you can compute from these probability distributions. And that's measurement specific. But then you can show that this is always lower bounded by something called the quantum Fisher information, and that only depends on the set of states. So no matter what measurement you do, you cannot get lower, so your error cannot get lower than 1 over this quantum Fisher information, or the inverse of the quantum Fisher information matrix. Okay, so I'm not going to give the definition of this. You can compute them from the probabilities with some derivatives, and this one as well. But in this talk, I'll mainly talk about pure states. So this is the simplest model you can think of. Just take a vector and rotate it with a unitary with generator G and some parameter theta. Yeah? So you just rotate it. And now the quantum Fisher information for this model, assuming that the mean of G is 0, so you can always choose G to have this property. Then the Fisher information is just the square of the derivative of psi with theta. So it's basically showing how fast the state is moving with the parameter, and that's the variance of the generator. So bigger variance, bigger Fisher information. Yeah? So this is important later on because we'll compute Fisher I'll show you the formula for the Fisher information for a Markov chain, and basically that's how we do it. Okay, now the simplest model you can think of, so more concretely, is a Gaussian shift model. So just take a CCR algebra. Yeah, so canonical commutation relations QP is equal to I identity. So you can represent this on the Fock space, which has this basis of vacuum state, one photon state, one excitation, and so on. In a simple way. And now consider this kind of states, which are called coherent states. They are Gaussian states of this algebra. you just take the vacuum state, so this first vector in that ladder, and you apply this shift with the momentum operator. And the constant here is the parameter u multiplied with something such that this model has quantum Fisher information f exactly. Okay, so you can represent this kind of states like this. So these are Gaussian states. They are determined by mean and variance of q and p. So this one has mean of q equal to this number, and mean of p equal to 0, and the variance of both q and p is 1/2, which is the vacuum variance. Yeah? So it's like you take the vacuum state and you displace it by this amount. And that's your Gaussian shift, because you are just shifting linearly with the parameter. And then the question is, yeah, how do I estimate this parameter? Well, it's pretty clear that this is the mean. This is basically the mean of q. So if you measure the canonical variable q, that should be a good measurement. So when you measure q, you get a normal distribution with mean and variance 1/2, which is the vacuum variance. So now if you take the outcome x, you get rid of this factor. You get something that has mean u, and then the variance of that will be f minus 1. So the inverse of the quantum Fisher information. So that means that the mean square error of this is going to be 1 over f. So it achieves the quantum Fisher information. So that bound that we said in the Kramer-Rao bound is achieved with this measurement. Okay, but kind of surprisingly, there is another measurement that also does pretty good. So if you just measure in the basis, in the Fock basis, you measure the number operator, which is something like q squared plus p squared minus 1, or something like that. So you just measure in the Fock basis, then what you get is a distribution, a discrete distribution whose probabilities are the squares of these coefficients, and that's the Poisson distribution. Yeah? So you get Poisson distribution with this intensity, and the intensity goes with u squared. Okay, and if you calculate the classical Fisher information for the Poisson distribution with this parameter in terms of u, then you will find that it is also f. So that measurement also achieves the quantum Fisher information. Okay, that's nice, because often maybe I cannot measure this q, but I can do photon counting rather than what people say homodyne in physics. And these are very different measurements. The first one has a continuous range of outcomes. The second one has a discrete range of outcomes. Okay, but there is a problem with the second measurement, is that it doesn't distinguish between this state and the state on the other side, which has mean minus u, because its intensity is u squared. Okay, so although locally it can, so if I knew that u is positive, that would be fine. But because it cannot distinguish between u and minus u, there is a non-identifiability problem with this measure. Okay, so we call this null measurements. So we have a lot of theory about this, not just for the Gaussian state, but we call them null measurements because you can think of it like this. So when the parameter is equal to 0, then you have the vacuum state, and the number operator will just give you 0. It's exactly, the state will be an eigenvector of the number operator with eigenvalue 0. You'll always get 0. And as you move away from the vacuum state, you will start to see other outcomes. So it's like a null. You try to, you could try to move the states towards 0, so you only see outcome 0. Okay, but how do we solve this non-identifiability problem? Well, you do it by using our displaced-null measurement strategy, which in this case is quite easy, but like I said, it can be used to estimate much more general pure models of this type. Okay, so suppose that I know for some reason that my parameter has some restricted range. So it's not completely unknown displacement over the whole line, but it's inside this ball, well, which means it's between here and here. Yeah. So I still have this problem that I cannot distinguish these two states. Okay? But what I can do is displace my state by a large amount. So if this ball has size m, I will displace it by m to the power 3. It doesn't really have to be m to the power 3, but it should be larger than m squared for some reason. And when I displace it, then the whole ball here will be on the positive side of the axis. So if I now count, if I do my counting measurement, yeah, there is a one-to-one correspondence between parameters and intensities. Yeah, there is no more ambiguity about plus and minus hue giving the same intensity. Okay, so that's very, very simple. And there is some bonus to doing this displacement and then doing counting, which is that if your displacement is large, so imagine this restriction m is actually, you almost don't know anything, but it's like a huge number, and then I displace by a huge number, okay? Then the Poisson distribution can be approximated by a Gaussian. So that's kind of known fact. You know, if you have a Poisson with very large intensity, you look at it, it's like a Gaussian. And using that, you can basically manipulate this Poisson outcome. You can rescale it and remove some bias to make it into a normal distribution with mean u and variance 1 over f, which is what we had in the beginning when we were measuring q here. Yeah? So although I'm not measuring q, I'm measuring n on a displaced state for large m. This is more or less the same. Okay? So that's one of the things I wanted to tell you. It's, there is no algebra here. I'm sorry, but it turns out to be important when we look at Markov processes. Okay, but now the actual typical problem in quantum statistics is not just measuring Gaussian states, but what people call state estimation or state tomography. So the setting is more like this. So you have an ensemble of quantum systems identically prepared. So if you want, your model is rho theta tensor n. And you are allowed to do some measurement on them. And then you want to estimate theta. Now, this measurement could be that you take each system and you measure it separately. That's what people can do in the lab. And there are lots of papers about what measurements to do and what errors you get. But mathematically, theoretically, you can make more general measurements that act on all the systems together and cannot be reduced to this kind of local measurements. These are collective measurements. And then the question is, yeah, how well can you do? What's the best measurement to apply in order to minimize the mean square error, say, of this estimator? And this is kind of difficult because yeah, it's a very large space of measurements. And our philosophy is that you shouldn't just look at measurements. You should look at the structure of this IID model. If you understand it, then you can find what's the optimal measurement to apply. And this understanding is something that people do in statistics for a long time. So this is inspired by the work of Lucien Lecam, who was a French statistician. And he developed this concept of local asymptotic normality. So local asymptotic normality basically means that if you have IID data, in some sense, is almost like central limit, but it's not central limit. In some sense, this model can be approximated by a much simpler model, which is this Gaussian shift model, where you just have a Gaussian with unknown mean and fixed variance. And that model is much simpler to analyze. And if you manage to control this approximation from your IID model to the Gaussian, then you can map the problem from your IID model into a problem of estimating a Gaussian distribution or parameter of a Gaussian distribution. So that's exactly what we do in the quantum case. So we take this IID model. Now this manipulation, this approximation is done via some quantum channel. So we send our systems through a quantum channel, and we send them in such a way that they get close to, so the state is close to a Gaussian. And then for that Gaussian, we know how to estimate optimally. I showed you for one parameter, but you can do it for arbitrary displacements with multiple parameter models. It's a more complicated kind of measurement, but it's still sort of linear. It's still more or less a measurement of Q's and P's. And from that measurement, you can get your estimator. Okay, so maybe let me just say in more detail how that works, because it's called local asymptotic normality. So what is local about it? So that approximation only works locally in the parameter space. So the idea is that if you are given n systems, yeah, you can use a small proportion of them, but still a very large number, if you think of this n as being large. Say n tilde is equal to n to 1 minus epsilon. You use them, and you do some stupid measurement, but good enough to estimate your parameter, with kind of standard precision. The standard precision is an error of the order 1 over square root of the number of systems. Yeah? So I get an estimator theta 0 such that you can get this kind of concentration bound, so the probability that theta minus theta 0 is larger than n to minus 1/2 plus epsilon is smaller than something, and that goes to 0 exponentially. So essentially, you have in your parameter space, if you use a few of the systems, you have localized your true parameter in a ball of size n to minus 1/2 plus epsilon around some preliminary estimator theta 0. Okay, so theta will be somewhere here with high probability. And then this asymptotic Gaussian approximation, you can show that it holds on a region that is larger than this. So all the parameters inside this ball where you know you are, you will be able to approximate your model by a Gaussian. So that's where LAN holds. And that's why I have here this local parameter being smaller than n to epsilon. Yeah.
Fix your epsilon stuff.
Sorry?
Fix your epsilon.
Yeah, you can fix your epsilon, yeah. Yeah, it's a technical thing, but it's important that local asymptotic normality doesn't hold for all parameters. It holds in this kind of shrinking neighborhoods, but that's enough for solving your estimation problem, at least asymptotically. So what's the Gaussian approximation? So if I now write my parameter as theta 0, so this preliminary estimator, plus a small deviation, which we said was the order n to minus 1/2 plus epsilon. So if I write it as u over square root of n, that means that u is going to be smaller than n to epsilon. Then there exist some channels, so CPTP maps, such that I can apply the channel Tn to all my states in that local neighborhood and get them close to a Gaussian state with mean u and some variance v0 in the trace norm uniformly over the local parameters, which I don't know, asymptotically with n. And the other way around, I can take the Gaussian with mean u, apply some quantum channel, and basically simulate my data, the IID state, in the limit of n to infinity. Okay, so this kind of convergence, this is what people call in statistics strong convergence. This is strong enough to prove, for example, to solve this problem of optimal estimation for states, because you can reduce it to this estimation of Gaussian mean. And the error that you make can be controlled through this, the fact that this norm 1 difference between the states goes to 0. Okay. But I'm not going to go into this. So we did this a long time ago. We did it for mixed states of finite dimensions. And more recently, we did it also for infinite dimensional pure models with pure states. There are also results for finite rank states in infinite dimensions, but there is nothing about infinite dimensional model without any sort of assumptions about the rank. Yeah? So there is still much more to be done in this direction of asymptotic normality with strong convergence. Okay, but I'm going to show you a sort of simpler way to see this, at least for pure states. So if I have my rotation model that I showed before, and I have n samples of this, and I have this state. And I can think of that state as being just a vector. Yeah, it's a vector in some Hilbert space. And now we said that we need to consider things in a local neighborhood of some theta 0 of size 1 over square root of n, roughly. So I'm going to look at the geometry of my model inside that little, so when I varied my parameter inside that little ball, and I'm going to take a one-dimensional parameter for simplicity. So now what is the geometry of a family of pure states? Well, it's completely determined by the inner products of the states. So if you take the inner products of the state with parameter theta 0 plus u over square root of n, you have n samples with the one with parameter theta 0 plus v over square root of n. Then you get the power n of this overlap, and because they are rotations, you get this thing here. And if you expand that, you get 1 minus the variance of g divided by 2n plus higher order terms to the power n, and this converges to e2 minus this thing, yeah? And, oh, I think I forgot here a u minus v squared. Sorry, there is a u minus v squared. So you get exactly this exponential u and the minus sign. U minus v squared times f over 8, so f was this, the variance of the generator. And this kernel is exactly the inner product of two coherent states with displacement this and this. Yeah? So you end up with the overlap of your coherent shift model. So from a geometric point of view, this model converges to this model. It's a different way of saying it. It's not as strong as the convergence through channels, which is something you can do operationally, but it kind of tells you that the same thing happens, and then you can think about how to strengthen this to get the other convergence and so on, but I'm not going to go into details. I just want to have this picture of what it means. Okay, so now I want to move to, okay, is there any question about this IID stuff? So, what's the, yeah?
In the land model, what do the channels look like? The TNs and the S?
Yes, that's a good question. So if you just take a qubit, two-dimensional system, and a pure state, then the channel is just an isometric embedding of, so you have C2 tensor n, you take the symmetric part of that, and you can embed it into the Fock space in a very simple way. So, yeah. If for mixed states, it's much more complicated, but you use the group theory. So your state is symmetric under permutations. So it will have a block decomposition into irreducible representations. And each of those blocks can be mapped into this Fock space. But that's a more complicated construction.
Sort of mixed unitary.
Yes, because you'll have blocks, there will be a classical component. So the probabilities of the blocks will have a Gaussian distribution over them. And each block will have some quantum Gaussian inside. Okay, so this is, very important setting in quantum technology. So Serge Haroche got Nobel Prize in Physics for this setup, where he has a cavity and there are atoms. So the atom maser, atom passing through the cavity, they interact with the field in the cavity. Then you can measure them as they come out, and then you can act on the cavity by some feedback operation to prepare a certain state. LIGO, there is also a Nobel Prize for the discovery of gravitational waves. This is also a sort of input-output system where you put some laser in this interferometer, and what comes out is measured, and you can sense disturbances in the space-time, whatever, gravitational waves, by doing that measurement. So both these things are called input-output systems. They also in quantum magnetometry, the same setup is used. So there is an input-output formalism that describes controlled open quantum dynamics. So open means that there is an open system, the cavity, because it interacts with the environment, which are these atoms. And a lot of this stuff is Markovian in some sense. So there is a lot of theory here that you can use, Markov semigroups, quantum stochastic calculus, quantum filtering, feedback control. So there is relation with engineering, control engineering and so on. And in control engineering, control and estimation or identification are kind of two sides of the same coin. So you can control the system if you know what's happening. Okay, so mathematically the setup is quite simple. I'm going to do it in discrete time, but you can do this also in continuous time. So you have a system which is d-dimensional, and then this is the input. The input is made of units that are k-dimensional, and they all come prepared in the same pure state chi. And what happens is that there is a unitary every time. At every time step, there is a unitary rotation on the system and one of the units, and then the system, so the units move, and the system interacts with the next unit, and then the next unit, and so on. Yeah. So, and then they come out, and this is the output, and that's what you can measure. So in the input-output theory, you don't look at the system directly, you look at the output and try to infer things from measuring this output state. So you need to understand what's the state of the system together with the output after n steps. And it's given by this. So you start with a product state, so system and all these input units. And then you apply these unitaries one by one, acting on system and each of these things. And you can write this in a basis, in a product basis of the output, like this. And here you get this, this kind of form, which is called the matrix product state. So you get a product of cross operators applied successively onto the initial state of the system with indices given by these indices of the basis. And the cross operators are just basically the expectations of the unitary on one side with the initial state of the input, and then the state on which you project the basis vector there. Okay, so you have this nice matrix product state. So this is very important in quantum information, tensor networks and matrix product states and all that. And my statistical problem is this unitary depends on some unknown parameter, and I want to estimate that. So that means that all these Krauses depend on some unknown parameter, and that's how it enters into the state. Okay, so this is a Markovian evolution in the sense that if you trace out, if you only look at the system, so you look at the state of the system after n steps, it's given by applying this transition operator, which is a channel, a CPTP map on the system. You apply it n times. Yeah, so that's Markovian property. And the channel is just this with the cross operators ki. And I'm going to assume that this is primitive, which means that it has a unique stationary state that is strictly positive, and it's aperiodic. So, there are some Perron-Frobenius theory about transition operators. And if this holds, then after long time, your initial state will always converge to that unique stationary state. So you have this ergodicity. And I'm going to assume that actually I've been watching this output for a very long time, and it has already gone into this stationary regime, no matter what the initial state was. And I'm interested to understand what is the stationary output state. So if my system is in the stationary state, it will produce a stationary output. That means if I shift my output in time, it will be the same state. and is given just by tracing out the system in this pure state. And how do I understand that state? It's not going to be pure, it's going to be mixed.
But
yeah.
Rho SS depends on theta or not?
Rho,
the stationary state, does it depend?
Okay, good point. Yes, it will depend on theta as well. Yeah. Okay. Well, but actually, the full state of system and output is pure. So I can, because it's pure, I can calculate this Fisher information with this variance of the generator or the derivative of psi square. And with a bit more work, you can show that also this output state will have the same Fisher information, at least in leading order in time. So if you trace out the system, you don't lose much information actually. And that's this theorem. So the quantum Fisher information for an output of length n will scale linearly with n, so it increases with n, and the limits of the rate is given by this kind of formula in terms of derivatives of Krauss's and the stationary state. And there is some interesting, Moore-Penrose, so some resolvent of the transition operator appearing in there. And there is some interesting stuff about when this Fisher information is large, because you have the inverse of this, that suggests that when you have a transition operator with small spectral gap, this Fisher information might blow up because you have the inverse of that in there. And small spectral gap means that you are near what physicists call a phase transition, so there is some relation with phase transitions and such things. So this is the formula for one parameter, but in fact we have done this with full parametrization, so all your unitary is unknown, so we understand that. This is called information geometry, and basically your quantum Fisher information in that case becomes a metric on the space of parameters, and it's a Riemannian metric on the space of identifiable parameters. So there will be some parameters that actually cannot be seen from the output, but if you quotient your space with those parameters, you get a proper Riemannian metric. And also you have asymptotic normality. So I'm going to show you on the next slide what this means. But you've seen it for IID. With pure states, basically the same thing holds here. If you take the system and output state, it becomes this. It satisfies that asymptotic normality property. So it's in some sense Gaussian or coherent state. But actually, there is so that's the stuff that we've done some time ago, but it's still very theoretical because we are just studying some statistical properties of this model. But if you go and do a standard sequential measurement, that's what people do in the experiment. You would measure each of these output units separately. That will give you some classical statistical model, and the Fisher information of that one will not be equal to the quantum Fisher information. So it will not be optimal. So typical standard sequential measurements do not achieve the quantum Fisher information. And that has been kind of an open, well, it has been an open problem for some time. How do you extract maximum information with simple measurements out of this kind of systems? So the asymptotic normality result is like exactly the same as in the IID case. You look in a neighborhood of some parameter theta 0 of this size, you write your parameter like this, and then you look at the overlap between the system plus output state after time n with this parameter and the output system plus output state with this parameter. And you compute that and you get that it converges to the overlap of two Gaussian states. Again, this is for one parameter. If you do it for multiple parameters, you will get an overlap of some coherent state on a multidimensional CCR algebra you can characterize. But here I'm focusing on one parameter. So the proof of this is So this is the idea. Oh, why? I didn't realize that this is not. Okay. Basically, using the Markov property, you can compute these overlaps, and they are just the expected value with respect to the initial state of the system of some power n of a sort of deformed transition operator. So now this is in the Heisenberg picture, so it's acts on observable. So you apply it to identity. And this deformed transition operator is like your usual some ki x ki, but now on one side you have a cross operator for the parameter v, and on the other side you have the cross operator for parameter u. And this is not completely positive anymore. Yeah? But you can show using Trotter-Kato theorem for perturbations of semigroups, and with a second order expansion of this, that this power n of this deformed transition operator on identity converges to a constant times identity. And this constant is exactly the overlap of these coherent states that you want. So that when you take expectation with phi, this identity becomes 1, and you get this number. Yeah? So it's a Trotter-Kato thing. Okay, now let's move to kind of more recent things. So we didn't know how to extract the quantum Fisher information with simple measurements, and simple means sequential. And the idea I had in this example with the Gaussian state was that you can try to measure the Q, the canonical variable, but you can also do optimally with counting. And when you do a counting measurement, the idea was that the vacuum state is an eigenstate of, is one of the vectors in the basis that you are measuring. Yeah? So I would like to somehow put my output state, so the output state is kind of in a wrong position with respect to my counting measurement. So I want to rotate it in such a way that the output state becomes like the vacuum in the case of the Gaussian model. So that when I do my counting measurement, that vacuum state is an eigenstate of my counting operator. Well, I'm not sure I explained that very well, but basically I want to do some post-processing of the output, a unitary, and then do my counting measurement as usual. And what is this post-processing? I'm going to use this thing called a quantum absorber. So after each of the units interacts with the system, I'm not going to let it go out. I'm going to let it interact with another system called the absorber with a certain unitary. And then it goes out. And now this unitary, this absorber has this property that basically, if I take my stationary state of the system, I can purify it, so I can construct a pure state of the system and absorber such that the partial state of the system is the stationary state. And this pure state is going to become the stationary state of this enlarged system under the new dynamics. So I apply first a U and then a V, so first this and then this. And if I put my system and absorber in this pure state, then it will remain in the pure state and the output will come out exactly as it came in. So there is no change in the input to the output state. Everything remains invariant. Yeah? So if you think of this as vacuum, this is also vacuum. And that's what I mean by the vacuum state was the nice state where you do a counting measurement and it's like the null state for that measurement. So what I have done is the output now is a vacuum, at least when this V is matched with U at a certain parameter value. Okay, there is a little problem because I don't know the parameter of U. So all I can do is to match this V at some guess. And at that guess, the output is going to be this vacuum. But as you move away from the guess, there will be a different state here. So there will be some kind of excitations. But that's exactly as what was happening in the model of the Gaussian state. When the parameter was 0, you have the vacuum state. As you move away, you have a coherent state with excitations. Yeah? Okay, so that's the setting I'm using, and now I'm going to measure. I'm just going to do counting in the output and hope for the best. And indeed, this works. And the idea is that because you are in a stationary regime, the output state is stationary in time. So the observables to look at, you guess that the best observables to look at are translationally invariant observables. And we are looking for something Gaussian because we know that the output state is Gaussian in some sense. So we are trying to construct a sort of CCR algebra of the output where our state lives as a Gaussian, as a coherent state. And this is done in the following way. So for each pattern, which is a sequence of 0 1s, which starts with a 1 and ends with a 1, we are going to construct some kind of creation operators that will become our creation and annihilation operators of this CCR algebra. So for example, if the pattern is just a single one, you just add all the raising operators of the so I'm using now the output unit is C2, and it has chi is equal to 0, so that's the vacuum, and the raising operator is sigma plus is just this, right? So it maps 0 into 1. And I sum over all my output units, so I smear this over all of them and rescale by 1 over square root of n for kind of central limit purposes. But I can do the same for other patterns. So if I have a 1-1 pattern, then I take the product of a raising operator on position I with a raising operator on position I plus 1. So they take tensor product, and you sum all of them and rescale, and that's another creation operator. For 1, 0, 1, I take sigma I plus and sigma I plus 2, so I put identity in between because there is a 0 here, and I smear all of this. Okay, and you can show that in the limit of large n, this, with respect to the product state of all this, the vacuum state, product of zeros, this becomes a CCR algebra where all these modes are independent. You have the usual Fock states where you apply certain creator with certain pattern a number of times and normalized by the usual factors. So this will be the number states in your, so the Fock basis. And the fact that it works, you can see it in this simple example. So for example, so here I have a state which has 2 excitation of type 1, and it's going to be applying this guy twice. So it will create a 1 somewhere and another 1 somewhere else, typically far away. And you compare with the state where you have a single excitation of type 1-1. So that will put 2 1s next to each other somewhere. And now if you look at the overlap of this is very small because these 2 1s have to be next to each other so that you get non-trivial overlap. So these states will become orthogonal, and this will be your Fock states. Okay, so now let me show you the main theorem, or one of the main theorems. So I try to argue that the output becomes this Fock space with respect to these modes. And now, how is this Fock space populated by my state that comes out from my absorber? If you have parameter theta 0, so if theta is exactly equal to theta 0, then we said that what comes out is exactly vacuum because they are matched exactly, so you have this nice property here. So you get vacuum. But if there is a mismatch in parameters, then there will be some different state coming out. And that state will be a coherent state in that Fock space of the translationally invariant modes. So the theorem is that if you look at the distribution of quadratures, so A plus A star, A minus A star, so the Q and P of these modes alpha, they all converge in distribution to normal variables as you expect for a coherent state with a certain mean and variance 1/2 because that's the vacuum variance. And the mean depends linearly on the unknown local parameter, and there is a constant, and this constant is related to the Fisher information in that state. Yeah? So for each of these alpha modes, you get displacement in a certain direction in the complex plane. Also, if you look at the distribution of the number operators, so if you are doing counting, then you get Poisson distribution, just like you expect for a coherent state with intensity U squared times this number squared. And the third thing is that if you sum up all the Fisher informations of all these modes, then you get the quantum Fisher information that we calculated earlier of the output, which means that these modes contain all the information about your parameter. So these modes are a subalgebra of the output in some sense. So in principle, it may happen that if you restrict to that subalgebra, some information is left out, but that's not the case. So all information is in this. Okay, and since I don't want to finish exactly at 0, so we can actually show that, so I'm not going to go in all the details on the last slides, but this theorem is still not very physical because how do I measure these number operators? I would like to measure the number operators because I know they are optimal. But how do I measure them? They are all sort of non-commuting operators on that output state. And the next result is actually showing that by just doing counting, you are effectively measuring those number operators. And that's kind of surprising. And yeah, to me, it was like a revelation. So if you just do counting, so you measure all these output units as they come out in the standard basis 0, 1. Yeah? Because your absorber is more or less matched to the parameter of the system, there is a little mismatch between them, so your state is going to be close to the vacuum state. You are going to be close to this 0, 0, 0 state. So you expect that you will see lots of zeros, but sometimes there will be ones, and they will come in these kind of clusters. And these are the patterns. So there will be a lot of zeros, and then some sequence 1, 0, 1, something, and then again lots of zeros. You can just extract these patterns. You can just put some buffer around the one and another one, lots of zeros around it. And you say, this is my pattern. And you can count how many patterns of type 1, how many patterns of type 1, 1, 1, 0, 1. Okay, so you get a probability distribution of such counts of patterns. So it's the sum of all possible trajectories which have that kind of count. And we can show that this probability of counts converges to exactly that joint Poisson distribution of all the modes alpha that we had before. So the joint distribution of all these guys is actually obtained by just doing counting, standard counting, and looking at this number of patterns. So it's just a Poisson distribution. Okay, and using this, then we can construct an estimator. So yeah, actually we checked in simulations because it's always good to see that it actually works. And you can see here for each of these pattern modes, this is a histogram of pattern counts for this type of pattern versus the theoretical prediction that is that it should have this intensity. Yeah. So this works. And then using this, we basically put together an estimator, which is a two-stage estimator. We first measure a small proportion of the output, just like we said in the IID case, just to get some rough preliminary estimator. Then we set the absorber to this preliminary estimator, but we displace it to avoid this non-identifiability problem that we had in the Gaussian case by some number. Then we collect patterns, we do standard measurement, collect patterns, and the optimal estimator is something very simple. It's just the preliminary thing plus a correction, and this correction depends just on the total number of patterns that you have in your trajectory. So not, more complicated dependence on which types of patterns and so on. Just the total number of patterns. And then we can show that this is indeed an estimator that achieves the quantum Fisher information, and is Gaussian. So this is like a histogram of the estimator, and this is the Gaussian with variance inverse of the quantum Fisher information. So it achieves our optimal bound. Okay, so just to kind of summarize, so local asymptotic normality was sort of the guiding principle for this. So for me, it was very useful to think in terms of these normal modes. How do I find them? How do I measure them? And so on. I think there is much more to do in LAN theory for quantum systems. So like infinite dimensional. Here in the Markov case, multi-dimensional parameters is not done. Continuous time, we are working on it. Mixed input states, I think is much more difficult, but it should hold. Infinite dimensional systems, strong LAN is kind of unfinished. Non-Markovian processes, non-parametric, so infinite number of parameters and so on. Okay, we use this coherent absorber trick to get optimal estimation with minimal sort of post-processing of the output. So we only apply a unitary to each output unit as it comes out. You could say, well, I can always do some huge unitary on the whole output and put it in a nice basis, but this is not what we do here. It's very simple. And the final estimator is based on this pattern counting. In physics, if you look in papers in quantum estimation, there is always some maximum likelihood estimator. But that's very difficult to compute. So maximum likelihood searches for the maximum of the likelihood over parameter space. Here, you just count patterns. Yeah? So this is very simple. There is a catch, which is that this works asymptotically. Yeah? So it kind of linearizes what your model asymptotically. If you have only few data, it doesn't work so well. Okay, so I'll finish here. Thank you.
We still have time for a couple of questions.
So for these LAN conversions results that you showed, is the conversions usually exponentially fast or?
Convergence to the LAN model.
Yeah.
Not exponential, it's polynomial. But it's some power of n, yeah.
Okay, this is optimal, or could you hope?
Well, I don't think, yeah, even in our papers, we don't really highlight the convergence rate. We just show that it goes to 0. But I think if you look in the details, you can get that it's this kind of power of n convergence. But that's actually important. If you are not interested just in asymptotics, but finite n kind of results. So Nilanja, sorry.
So in quantum input-output system, we made this assumption that the transition operator was primitive, and anything we said, and it's not.
Yes. Yeah, so we have a paper with Federico where we look at reducible systems. So if you have two invariant states, in that case, you can get this sort of Heisenberg scaling property of the quantum Fisher information where it goes like n squared instead of n. So we study that situation kind of completely. So it's quite different behavior, but this n squared behavior is very sensitive. So if you trace out the system, you lose the n squared and you go back to a linear scaling. So it's only in the system and output scaling that you get this Heisenberg. But we looked at that. But more interesting, there is the situation where you allow for periodicity. So we are also doing this work now, and there is some interesting stuff happening that you get not only asymptotically normal stuff, but you get also mixtures of this Gaussian stuff. So the periodicity sort of acts on the Gaussian limit and it mixes it up. And you get some interesting models.
Let's save more questions for later. Thank you.